Is x equals -2 a solution to this inequality? So all we have to do really is just, since they already give us a possible solution, we're going to go place it in all the x's and see if we get a true statement or not. So plug in -2 and we get -4 plus 3 greater or equal to 3, and that gives us -1 is greater or equal to 3. Now, is -1 greater or equal to 3? That's a big no, so the answer is no, that's not going to be a solution to this inequality. Next example, we are supposed to solve this symbolically or algebraically, so I'm going to isolate x and maybe start off with the 10x's. That's 14x minus 6 greater than 12. Add 6 and we get 14x greater than 18. I divide by a positive number so I don't have to flip the inequality. It looks like they're both divisible by 9, or by 2, I'm sorry, so that's going to be 9 over 7. So in set notation, x such that x is greater than 9/7. So all the values of x bigger than 9/7 will work for this inequality. It has infinitely many solutions. And anything smaller than 9/7 or equal to 9/7 will not work for this inequality. Part B, I see some fractions, so I'm going to go ahead and multiply each chunk by 5 to get rid of that fraction. The fractions greater or equal to -25. And since I multiplied by a positive number, I don't have to flip the inequality. I'm going to add 1, we got 4x greater or equal to -24. Divide by 4, and again, I don't have to flip the inequality because I divided by a positive number. So our solution is x such that x is greater or equal to -6. Okay, part C, we have x minus 5x plus 3 less than 2x minus 1. Combining like terms, -4x plus 3 is less than 2x minus 1. If I want the x's on the left, for example, that's going to give me -6x plus 3 less than -1. Subtract 3, and I'm getting -6x minus 4. Less than -4. So I have -6x less than -4, and notice here if I divide by -6, I'm the one dividing by -6, so it flips inequality, and then I can divide top and bottom by 2 and get a 2/3. So ultimately my solution is x such that x is greater than 2/3. In example 3, we have to solve using the table, so they want us to fill the table first. An x value of 2 plugged in here. I'll do it for this one, show the work. 2 times, or -2 times 2 plus 6 is going to give us -4 plus 6, which is a 2. So similarly, we fill the rest of the table by plugging in the values. Now that I have the table filled, I go back and I look at my original inequality, which says, when is -2x plus 6 less than or equal to 0? So here is -2x plus 6, and I look at the first case, is 4 less than or equal to 0? That's a no. Is 2 less than or equal to 0? That's a no. Is 0 less than or equal to 0? And that's a yes, because 0 is equal to 0. Is -2 smaller or less than 0? That's a yes. And is -4 smaller than 0? And that's a yes. So everything from this point on satisfies having an output that's smaller or equal to 0. So these are all my solutions, and anything to the left of 3 is no good. So just by looking at the table, I know that my solution is x such that x is bigger or equal to 3. Again, I didn't algebraically or symbolically solve the inequality, I just looked at the table, and if I had to, I could go ahead and solve it symbolically as well, just to make sure. And it does. If you look at it, you're dividing by a negative, so you're going to flip the inequality. It matches up with the solution we found from the table. Part 2, we do the same thing, so we plug in 0, and it looks like we get a -1, and we do the rest for the rest of the table. So once we fill the table, we go back and analyze what the problem is asking. The quantity 3x minus 1 has to be less than 8. So here's the quantity 3x minus 1, and all these outputs that are less than 8 qualify for my answer. So this is less than 8, yes. This is less than 8, it's a 2, yes. This is less than 8, it's a 5, yes. Is 8 less than 8? That would be a no, that wouldn't qualify. And is 11 less than 8? And that would be a no, and that would be disqualified as well. So it looks like everything to the left of 2 is good, but I have to be careful because this is a less than problem. There are values between 2 and 3 that would also qualify. So anything at 3 is basically sort of the border, and all the x values to the left of 3 seem to give me an output that qualifies for this problem. Like 2.999, if I put it in, it'll give me something smaller than 8. So the border is sort of at 3, and anything to the left of 3 would work. So my solution here would be x such that, let's do it in red instead, x such that x is less than 3 in this case. And again, I can quickly test that doing it algebraically as well, or symbolically. That's going to give me, I don't have to flip the inequality, x is less than 3, which is the same thing I got from the table. Okay, so we did inequalities symbolically, where we used algebra to solve it. Then we did it with a table, where we analyzed the table, and now we're going to solve inequalities with a graph. So this graph is given to us, and we're supposed to use the graph to find when y1 is equal to 0. Well, y1 is this graph of the line they give us, and we know the y value being 0 for this line occurs right here because it goes through the ordered pair -1, 0. So when is y1, when is that line containing a y value of 0? It happens at the x value -1. So our solution for that is x such that x is equal to -1. That's when it'll have a y value that's equal to 0. The next piece says, when is y1 less than 0? In other words, when are all the y values negative? Because if they're less than 0, they must be negative. And I can look at my graph and analyze that this right here signifies all the y values that are less than 0. So what x values qualify for those y values? Well, if I look up at my x-axis, anything to the left of -1 gives me those negative y values. So x such that x is less than -1, the borderline in other words, is going to give me all the y values that are less than 0. Similarly, when are the y values positive? When are they bigger than 0? So if I look at my graph, right here, all the y values are bigger than 0, they are positive. When do those occur? Well, they all occur on these x values that are to the right of -1. So all these x values contribute to those positive y values, which means the solution to when y is positive is x such that x is greater than -1. So if you graphically analyze it, y is 0 at -1, and then y is negative or smaller than 0 at all these x values. It's as if this portion of the line casts a shadow on the x-axis to the left of -1, and y is bigger than 0 or positive as if this portion casts a shadow at all the x values that are to the right of -1, or x is greater than -1. Let's go do the same thing for part B. Again, this is very visual. We don't have to do any algebra to get it. When is y equal to 0? Well, y is 0 right here. It's basically the x-intercept of this graph. that occurs at 2, 0. So x such that x is equal to 2 gives me a y value of 0 as indicated here. When are the y values less than 0 or negative? Well, all those y values that are less than 0 or negative occur right here, and those are associated with all these x values. These x values are the ones that create this negative y values. So my solution for all the y's being negative must be x such that x is less than 2. They're all to the left of this ordered pair 2, 0. When are the y values greater than 0? Well, the y values are positive or greater than 0 right here up above, and those cast a shadow down here on the x-axis for everything to the right of this point, which is 2, 0. So my solution is all the x such that x is greater than 2.